And now we're going to go on to our third presentation for this morning's plenary. And this is going to be about a nicer view, physics and astrophysics from the International Space Station by Zaven, Arzoumanian. Thank you very much.
Thank you.
Good morning, everybody, and thank you, Deirdre. Thank you also to the organizers. I'm very grateful for the opportunity to talk to you this morning about the NICER mission. NICER is the Neutron Star Interior Composition Explorer. It's an X-ray observatory mounted on the International Space Station, and it's dedicated, I shouldn't say dedicated, its chief science motivation is the study of neutron stars and other X-ray emitting cosmic objects. Now, before we dive into the science, I thought a little bit of context might be appropriate. And so welcome to the International Space Station. The space station is about the size of a football field. It orbits the Earth every 90 minutes, about 250 miles overhead. You could get there in about 4 hours if you could drive your car straight up into the sky. This picture was taken from a space shuttle about a decade ago. And if I could draw your attention to the structure down here on the starboard side, in this picture, space station is flying out of our screens towards us. And at the base of the solar panels, the next picture zooms in here on the starboard side. A couple of astronauts have kindly stepped outside to give us a sense of scale. And those of you who are fond of cosmic rays might recognize the alpha magnetic spectrometer down here. NICER, which doesn't appear in this photo, is currently installed just past the right shoulder of this astronaut, hovering right of center here in the photo. And that's shown in this computer visualization. As you can see, NICER is a moving payload. It's a collection of telescopes mounted over an elevation over azimuth gimbal. And the solar panels are in fact quite close. Each one is about as tall as a 7-story building. So we are constantly playing a game of peekaboo with those solar panels to get a good view of the sky. Fortunately, being on space station, unlike other space-based observatories, we don't have to rely just on computer animations and illustrations. We have photos. This was taken by NASA astronaut Drew Feustel a year and a half ago as he and his crewmates were departing on a Soyuz spacecraft. In this photo, we're looking at the aft, from the aft direction, so space station is flying away from us. And there's NICER, again, on the starboard side at the base of the solar panels. We also have occasionally live video from outside the space station. This is sped up by about a factor of 60 compared to real time. You can see the movement of the giant solar panels and the way that NICER slews between targets and then tracks them as they go overhead, rising in the forward direction and setting in the aft direction. So this is a great joy for us to be able to watch our photons being collected sometimes in real time. Of course, none of this would be possible without a brilliant team, including scientists, engineers, operations folks, technicians, support staff. And we're grateful to all of them for everything they've done to make NICER possible. NICER was launched almost 3 years ago in the summer of 2017 on a SpaceX resupply flight to the space station. It doesn't involve astronauts in any way. The installation was done robotically and the operations are done from the ground at NASA's Goddard Space Flight Center. And we've been operating smoothly now for almost 3 years. And our key science, as I mentioned, is to understand the structure, the dynamics, and the energetics of neutron stars. I won't be able to say very much about the hardware today. There just isn't time. I won't delve into too much science outside of neutron stars either. But just to give you a very brief overview of the mission, our principal investigator is Keith Gendro at NASA Goddard. I'm his deputy and the science lead for the mission. The platform on which we're attached is called an express logistics carrier. There are 4 of them on space station. As you saw in the animations and the video, we are actively pointed. NICER can see virtually the entire hemisphere centered on the zenith, so a good sky coverage, except of course where the solar panels are. The instrument itself is a collection of X-ray optics that we call concentrators. They function in the soft X-ray band between 0.2 and 12 keV photon energies. And each of the optics is paired with its own detector, and they're all co-aligned to good precision to view a patch of sky that's about 6 arc minutes in diameter. NICER also includes a GPS receiver so that we have position and absolute timestamps for the X-rays that are detected. It is a photon counting instrument, so we detect individual X-ray photons and we assign timestamps to them. Those timestamps are good to better than 100 nanoseconds. And so we're able to look at very, very rapid phenomena with good sensitivity. Our current status is that the payload's performing very well. There's already a substantial archive of public data, which I encourage everyone to dive into. There's an aspect of the mission that is burbling along in the background, which has to do with demonstrating spacecraft navigation using pulsar signals as sort of a natural galactic GPS. That was successfully done early on in the mission, and I won't be able to say much about it today, but I'm happy to take questions or refer folks to published work. NICER was originally launched for an 18-month mission. We were fortunate to have a 3-year extension until the next Astrophysics senior review at NASA headquarters, which will take place in 2022. In the meantime, we're operating as a guest observer facility, doing peer-reviewed observations that are proposed by an international community of observers. So what's all the fuss about neutron stars? Why do we care, and what are we learning? Of course, neutron stars are extreme objects, extraordinary in every way. Gravitationally, they are sort of poor cousins to black holes, so it's tempting, I think, sometimes to say, well, sure, they have strong gravity, but they don't have event horizons, so boring. But in fact, there's lots more going on. They can crush up to 2 solar masses worth of matter into a space that is about the size of a city. Here you see a cartoon neutron star hovering over the San Francisco Bay Area. They're the most rapidly rotating stars known, hundreds of times per second spinning on their axes. They're the strongest magnets known, anywhere from 10 to the 8 to 10 to the 15 Gauss, so trillion times stronger than the Earth's magnetic field. They're the fastest moving stars in the galaxy, 1,000 or more kilometers per second in some cases. And of course, because of the extreme densities, they harbor the highest density matter known anywhere, and matter that can't be reproduced in any laboratory or anywhere near the solar system, thankfully. This is actually a significant fact because if you'll forgive a tortured analogy, if you think of gravitational collapse as being like a river where the event horizon is a waterfall at the end of the river from which there's no return, neutron stars are sort of the last port of call, the last dock at which matter can stop and stably exist. After that point, if you presumably add a small amount of matter to a neutron star that's at the cusp of further collapse to a black hole, then that matter is doomed to eternal collapse, whatever that might actually mean in practice. So understanding this sort of natural limit to stable density is a fundamental problem that's been around since neutron stars were first proposed in 1934, just 2 years after the discovery of the particle, the neutron. So that the theoretical question remains, just what is inside a neutron star? Observationally, we have this handle that they are cosmic lighthouses. We see beams of rotating radiation across the electromagnetic spectrum from their surfaces and from their magnetospheres. And those allow us to see pulsations as the beams sweep across our line of sight. And it turns out that those sweeping beams reflect a very precise clock, a very precise and stable rotation that can be exploited in ways that I will describe to understand the interior composition of neutron stars, and so the nature of dense matter at the cusp of collapse to a black hole. This cartoon shows the giant question mark in the core of the star, and that indeed is what we intend to address and are addressing with NICER. There are a few more details here. As you can see, there's some quite astonishing phenomena that go on as you go further down into the star, including superfluid neutrons, superconducting protons on stellar mass scales. And then as you get to near to the center of the star, densities that exceed twice the nuclear saturation density, and a real mystery about how matter behaves. This is a simplified picture of extreme cases where you could imagine at the core of the star having true nucleons, recognizable neutrons and protons that are collections of the usual 3 quarks. Or, and in that case, you'd have a stiff core where the nucleons are bumping against each other like marbles. And that stiff core is able to support the pressure from the outer layers of the star, and you end up with a larger star. And at the other extreme, you could imagine having a soup of quarks and gluons, perhaps including even strange quarks, the more massive versions of the up and down quarks that make up normal matter that we see around us. In that case, you'd have more of a squishy core, and that wouldn't be able to support the pressure from the outer layers, and you'd have a smaller star. So for a given mass, the radius of the star is a very good handle on the interior density and the composition of the interior, or at least what we call the equation of state, the relationship of pressure to energy density in the interior of dense matter. That relationship is shown on the left here, or a collection of large number of representative, not complete, but representative proposed equations of state across a range of densities. The vertical band shows the nuclear saturation density. And all of these have remained viable for decades without very strong observational constraints at high density. They are founded, of course, on experiments at low density, accelerator experiments, and other nuclear physics considerations. But at high density, there's been not much in the way of constraints. Given a favored theory of gravity, like general relativity, one can map a given pressure density relationship on the left to a mass radius relationship on the right for a neutron star. And here, the different colors represent different assumptions about the makeup of the interior, which quarks and gluons, whether you have hadrons or protons, neutrons, as we would recognize them in normal matter. It turns out that through the benefit, excuse me, of having a strongly self-gravitating object, one can take advantage of the surface emissions of a neutron star to probe the interior, as I've mentioned. And our simulations suggest that we can do much better than 10% mass and radius constraints if we could collect about 1 million photons from the thermal emission from the surface and watch its modulation as the star spins. NICER was designed to do just that. If you imagine a beach ball on the left, something with very weak gravity, and a hot spot on its surface rotating, to a distant viewer, to a distant observer, that hot spot appears when it's on the same side of the star as the observer, and then disappears when it's on the far side. And so you get a deeply modulated light curve or pulse profile here on the left. But if gravity is strong, as it is for neutron stars and black holes, there's a distortion because some of the light emitted from the backside of the star is actually lensed around by the gravity of the star and reaches the distant observer. And you can see from the grid lines of the globe on the right that we're seeing some of the far side of the star. And depending on where the hotspot is, we can see some of its emission even when it's on the far side. And the star correspondingly looks bigger as a result of that lensing. And the pulse profile or light curve is significantly modified from what it would be for a weak gravity case. The shape and to zeroth order, the modulated fraction tells us what the mass to radius ratio of the star is, what we call the compactness, m over r. This visualization is just showing us a picture that doesn't depend on the photon energy. Gravitational light bending is achromatic. We see the same effect regardless of photon energy. But if you have instead the capability to measure photon energies, you get additional information which you can use to separately constrain mass and radius. So in fact, NICER is designed to collect data that looks something like this simulated picture on the left for the nearby pulsar J0437, which is sort of the poster child for this technique. Pulse phase, the rotational phase, is on the horizontal axis, and the photon energy, the spectrum, is on the vertical axis. So we're talking about doing phase result spectroscopy on millisecond, sub-millisecond timescales. Now, sadly, there are no millisecond pulsars bright enough to get this quality of data in a single 5 millisecond rotation. We have to accumulate data for approximately 1 million seconds, in this case, a megasecond of exposure, to collect the signal to noise ratio and the 10 to the 5 or 6 photons that we need to get the mass radius constraints that we're interested in. With absolute timestamping of the photons, we can do this and coherently integrate, coherently with the pulsar spin, integrate data over the mission lifetime for any number of millisecond pulsars. The reason the photon energy is helpful is because neutron stars have atmospheres. They're about a centimeter thick, but they are dense enough to modify the emergent radiation, the photon spectrum that reaches an observer at infinity. And that photon spectrum is sensitive to the gravitational acceleration, the local acceleration at the surface, which is a function of m over r squared. And that's how we can separate having one effect that's dependent on m over r and another effect that's dependent on m over r squared, and two measurables, namely the light curve shape with the rotation of the star and the spectrum, we can ultimately separate mass and radius. There are, of course, unknowns. The model is complex. Among other things, we aren't entirely sure whether the atmosphere is fully ionized or partially ionized, whether it's pure hydrogen or whether there's some amount of helium mixed in. There are potentially uncertainties about the relativistic light bending calculations that have to be done many, many millions of times. And so we have to use shortcuts, approximations, and give up a little bit of numerical accuracy in order to do the number of computations that have to be done to fit, to generate template light curves and match them to the observed light curves, to pulse profiles. And so here I've listed some of the uncertainties in our modeling with check marks where I think we have a quite good handle on our ability to account for those uncertainties. And some aspects, such as the sizes and shapes of the polar caps and the geometry of our view onto the star and the magnetic axis orientation relative to the spin axis, where we have to rely on the model and the fitting to provide that information because we don't have it a priori. There are other aspects like instrument calibration and the background X-ray counts in our data sets that also have to be either provided a priori or allow the fit to accommodate the residual uncertainty that we have in calibration and X-ray background modeling. And so those further complicate the fitting procedure, but it is a tractable, so far it has been a tractable problem. This slide just shows some of the geometrical considerations. Here's the pulsar spin axis. The blue line going out to infinity is the observer's line of sight. The hot spot is the optimistically small black dot on the surface here. The red shows a gravitationally bent ray departing the surface at some angle theta with the normal, where the hot spot makes some angle alpha in this notation from the spin axis, and the viewer makes an angle zeta. All of these things matter significantly to the shape of the light curve as originally spelled out by Bogdanov, Rybicki, and Josh Grinley. And as you can see, the modulation changes significantly depending on what this geometry is, and it's a fixed geometry, thankfully, so we can again accumulate data for long periods of time for a given pulsar. And then, of course, coming back again to the uncertainty about the hotspot shapes, I should say that the surface hotspots are generated by currents, magnetospheric currents in these very, very strong magnetic fields, some of which return down to the surface, raining down from the magnetosphere, electrons and positrons, and heating the foot point of the magnetic field where it impacts the surface. And the temperatures and the sizes and shapes of these foot points, these polar caps, have been the subject of considerable study, but ultimately we prefer to be agnostic and allow the data to inform us about what the shapes and sizes and temperatures of those hotspots should be. So we begin with the simplest assumptions, for example, of a star-centered dipolar magnetic field with two equal hotspots on either side of the star, antipodal, with uniform temperatures. And we find that that's the scenario here in the leftmost column. And we find that that's simply not a good description of the data. We then try to add temperature variations across the spots. For example, having an annular configuration with a hot core and a cool periphery for each polar cap. and when that doesn't adequately describe the data, we start moving the two components, the hot and cold components, around. Sometimes having an asymmetric, non-concentric or eccentric configuration with a hot core and a cool periphery, or vice versa, and sometimes allowing the core to expand and actually overtake the periphery, and in which case you get sort of arc or crescent shaped configurations. This is obviously increasingly complex with more parameters being added to the model, and we can continue ad nauseum, but with adding complexity. Thankfully, the Bayesian inference process tells us about how much evidence the data contain and how complex the model needs to be to describe the data adequately without being unnecessarily complex with too many parameters. The images I've just shown are the work of one subgroup within the NICER science team. For robustness and to make sure that we covered many bases of different approaches, one group out of Amsterdam made their favored assumptions about data filtering and spot shapes and so on, and used their own developed code. And another group based at the University of Maryland and University of Illinois led an effort with their own code and their own assumptions about spot shapes and sizes. Here's some of the data, actual data from NICER for 4 pulsars, of 4 out of 6 or 7 that we're currently pushing with very deep exposures. I'll be talking about results from this one here at upper right, J0030. The others are still in work, and we have good things to look forward to this year. This is the work by the Amsterdam group, Tom Riley et al., paper published in December on the left. The top panel shows the data that you've just seen, the model in the middle panel, and the residuals, so there's a good fit. Cole Miller's, the effort that was led by Cole Miller here shows a simpler distillation of the data, just a bolometric light curve, and the data fit and the residuals for this pulsars data set. After turning the crank many times, the two groups' results are shown in the movie here at upper left, where the Amsterdam result is shown on the left, and that requires a single small hotspot on one side of the star and a large arc crescent on the other side of the star, both of which are in the hemisphere away from us, the viewer, what we arbitrarily call the southern hemisphere. And given that configuration, there's a mass and radius constraint at the approximately 10% level that are very interesting and the first of their kind. As the bullet points here tell you, we've measured mass and radius for the same star for the first time. In fact, this is the first time a mass has been measured for an isolated, non-binary neutron star. We've made the first heat maps, temperature maps of neutron star surfaces, and found that they're not at all dipolar. This is the equivalent result for the Illinois-Maryland group, where in the top row you see 2 spots, again, one extended and one compact, with the observer shown by the heavy line here at the top. The lower row show a 3-spot model, which is marginally preferred over the 2-spot model, where the 3rd spot is nearly coincident with the south rotational pole. It's not clear that that's really strongly preferred, but in any case, the mass and radius that come out of this modeling are entirely consistent with the Amsterdam model. So I'm running out of time. I'll be very brief. The available result at the 10% level for mass and radius from pulsar J0030 from NICER chips away at the prior information in pressure versus energy density, or number density in this case. Given priors and including the fact that there are two pulsars known with two solar masses, and the LIGO double neutron star merger event, we find that in a certain range of densities, the nicer result tightens up the empirically measured now pressure density relationship by something like 30%. And there's good prospects for further improving that. Here's the same thing on the mass radius diagram using contours from the Miller et al. Result. As you can see, it begins to rule out some of the strange quark matter, some of the softest equations of state. We anticipate being able to shrink these contours significantly with additional data from pulsar J0030, but also, and very intriguingly, pulsar J0437 should give us 5% or better measurements in both radius and the mass that is already known from radio pulsar timing. And it's got a comparable mass, about 1.4 solar masses, so we'll be interested to see how those contours fill in. And then we have two high mass pulsars up at the 2 solar mass level, for which at a minimum we'll be able to get lower bounds on the radius. They're quite dim. We may not be able to get closed contours, but depending on what those lower bounds turn out to be, we could be ruling out a substantial phase space there. Here are some of the nicer pulse profiles for additional pulsars. This is also published work in 2019 by Sébastien Guyot. Two of these pulsars have been promoted to the light curve modeling effort, one of which has a known pulsar mass from radio timing. The red traces here show the radio pulse profiles compared to the X-ray pulse profiles. And there's a variety of correlated and completely uncorrelated behaviors that is not really well understood at this point. Here are the two massive pulsars. I'll just move on. Anyway, the summary of the key science is that we have a substantial amount of data, as I've mentioned. We have good mass radius constraints for the first time and expect to publish more this year. The big surprise, among other things, is that the traditional canonical model of a star-centered dipolar magnetic field appears to be quite robustly ruled out. And there's new evidence for either multipolar or other complexities in the magnetic configurations of these neutron stars. And that sort of redraws the magnetic field diagrams and rewrites the textbooks for that. And so, of course, the internet wasted no time in pointing out to us that our logo was flawed and needed to be revised. We haven't taken that step officially, but thank you to whoever did that. I was going to say more about neutron stars, X-ray bursts, and so on, but I've run out of time. So I will, at this point, take questions. Thank you very much for your attention.
Thank you. Thank you for that lovely talk. Let's go to questions. And everyone, all the speakers, you'll find that you've all been applauded quietly on the chat window, so you don't feel like you haven't been appreciated. So we'll start with Robert, who asks, to what extent would the rotation create an oblate spheroid such that the proton atmosphere grows azimuthally to the equator?
The rotation does, in fact, distort the star to an oblate shape, and that is taken into account in our ray tracing. It also changes the local gravitational acceleration, the m/r squared, at the location of the emission of the photon. This plot here at the upper right, the OS, stands for oblate Schwarzschild, and that's in fact the space-time that we use outside. Well, the space-time outside the surface of the star is still assumed to be Schwarzschild with Doppler effects tacked on, but the surface of the star is taken to be oblate based on work that was done by Sharon Morsink and collaborators several years ago.
Thank you. The next question is from Quinn, and he asks, has NICER found any evidence for or against a phase shift in neutron matter at high densities compared to what we see at low densities?
I think it's too early to say. We could hope to see such a shift, such an effect, when we have fully analyzed the data that we're collecting now for the highest mass pulsars known, the 2 solar mass objects.
Our next question is from Salvatore. He asks, what's the lifetime of the hotspots? Can you treat them as having the same identical shape and properties for the duration of the measurements? Have you allowed for time-dependent hotspots and got Bayes factors against time variability?
The answer to the first part of the question is, as far as we can tell, yes, we can assume that the hotspots are constant over eons, especially for these millisecond rotating pulsars, which are extremely old and show no variation. There isn't a single case where we see any evolution in time now after 30 plus years of millisecond pulsar radio observations, except for those cases where geodetic precession in relativistic binary pulsars is important, where we can actually see the spin axis of the pulsar precessing over the span of years in a handful of cases, maybe only 2 or 3. But for the objects that we're looking at, those effects should be minimal. And in fact, we have broken the data set into 2 parts, the first year and the second year, and analyzed them independently, and we see no evidence for any kind of change spectrally or in the pulse profile, the light curve.
Okay, and the last question comes from Michael, who asked, does some of the equation of state models include dark matter effects? If so, how have these models been constrained?
None of the models that I'm aware of, but I'm not a nuclear physicist so far, include dark matter. But I know that, for example, Chanda Prescott-Weinstein at University of New Hampshire is very keen on addressing that, and we will be soon. The differences between normal matter and dark matter equations of state may not be very big, but I honestly don't know. And so we'll see how well our 5 to 10% mass radius constraints can distinguish between those kinds of different models.
Thank you for that, for answering all those questions. I think we got all the ones that were available in the chat window. I also want to thank everybody at this time, not just Zaven for this great talk, but Laura, Helmi, and Amina, and Michael, a little happy birthday to Physical Review from everybody on the chat. And thank you for attending this session. We had at some point almost 550 people participating this morning. And the talks were great, and I thank you all for sharing them with us today.